Welcome to the office. We want to take a look at an example of classifying a quotient group based on the fundamental theorem for finitely generated abelian groups. We're going to approach this problem similar to how we approached the last problem. In particular, what we're going to do is find the order of the factor group or quotient group by first finding the order of the normal subgroup. And the group itself, of course, right? So since our group Z9 direct product with Z15 is itself a finite group of order 9 times 15, 135 that is, since we have a finite group, we can go ahead and use this idea that the order of that group is the product of the order of this normal subgroup with the, this order of this is equal to this times the index of this in there. That's what we had in our last video. So in particular, what I want to do is I want to find the order of this subgroup, which is equivalent to say I'm looking for the order of this element. The process of finding an order of that element is to determine the order of the individual pieces and find that least common multiple. So the order of 3 in Z9 is 3. The order of 5 in Z15 is also 3. Awesome. Mostly. Certainly they can be the same thing, though they don't have to be. The order of the element 3, 5, or the order of this subgroup, either way you say that is absolutely fine. The order of this in Z3 direct product with Z15. I'm sorry, that's supposed to be Z9. Z9 direct product with Z15 is the least common multiple of those two orders themselves, 3 and 3, but that, of course, is 3. This tells us, essentially right away, we should be able to recognize that the order of Z9 direct product with Z15 mod what's generated by 3, 5, the order of this is equal to the order of the group Z9 direct product with Z15, which is that 135, and then divide by the order of that subgroup, which is 3. That's going to give us an order of 45. Now, having an order of 45 is not quite as convenient as the previous example. The previous example, we were able to say, oh, look, 6. An order of 6 can only be obtained by the product of 2 and 3, which means that this had to be isomorphic to Z2 direct product with Z3. Okay, that was a previous example. Here we have that this is 9 times 5, or what we can observe as 3 times 3 times 5. And by writing it this way, we recognize that our possibilities are, so if I call this thing G mod n for simplistic notation here, G mod n is isomorphic to Z9 direct product with Z5, or it's isomorphic to Z3 direct product with Z3 direct product with Z5. So these are our options. And how do we determine which one is correct? Well, all we need to do is consider the order of the elements. This group here, for example, contains elements of order 9, right? The generator for Z9. Oh, right, paired with the identity here, for example. Here we have elements of order 3, and we have elements of order 5, and we have elements of order 15, but we do not have any elements of order 9. So contains elements order 9, and this one does not contain elements order 9. So if we can find an element of order 9, then we can immediately conclude that, yes, indeed, we have that this is isomorphic to Z9 direct product with Z5. If we can't find any elements, right, we either have to exhaust all possibilities, right? The identity itself is not order 9 clearly. So of the remaining 44 options, we would have to verify that all 44 of those do not have order 9. In order to conclude this, or find one that is order 9 to conclude this. So there might be a better way to go about it, but I also am quite confident that we can consider the element 1, 0 plus the normal subgroup 3, 5, right? That's how we express elements in the quotient group, element times or plus the normal subgroup, right? So this is our coset. I believe this is order 9. So if you're happy with this, this tells us that Z9 direct product with Z15 quotient by 3, 5 is isomorphic to Z9 direct product with Z5. Okay, so that's what we're looking for there. The only thing that we would have to do beyond this is go ahead and verify that this element is order 9. That would be a wise choice for us to do. So I'm going to do that. If you don't want to see it, hopefully I'm not wrong, right? That's probably the main thing right now. So I want to take 1, 0 plus 3, 5. And what I want to do actually maybe is recognize that 3, 5 itself is the set 0, 0, 3, 5. And I said it's order 3, so I'm expecting to get exactly one more thing here. So 6, 10, and then it would be back to 0, 0. So if I find any one of these things as I'm working through, then I would end up with something right that belongs in here and is then 0. So 2 times, let's see if I call it element. Well, that's not given a name. First order, second order to 0 plus, run raise it to the second power, take 2 times this thing. I could try to rewrite this, but it's not going to give me anything that's in there. So 3, 3, 0, 4 is going to give me 4, 0. 5 is going to give me 5, 0. 6 is going to give me 6, 0. 7 is going to give me 7, 0. Right? I have all of these things still here as well, because these are all cosets. If I move up to 8, that's going to give me 8, 0 plus what's generated by 3, 5. And then finally 9. 8 plus 1 gives me 9. 9 in Z9 is 0, so that results in 0, 0, which of course is in what's generated by 3, 5. So this is equal to just 3, 5. So this element here does have order 9. Therefore, we do have this isomorphism here. And this is exactly what we were looking for. So excellent. If you want to state with confidence that you believe this is order 9, right, in your homework, hey, this is order whatever, so we can conclude this. That's fine. And as long as you're correct, I won't complain too much, especially on exams, right? But if you don't verify it and you happen to be wrong, then there might be some issues there. So That's all I wanted for this example. We've got more examples to consider, so join me back in the office in just a moment.